Today, we're going to look at topics 2.4 to 2.6, exponential manipulation, modeling, and validation. Looking at topics including all the exponent laws, residuals, and how to model exponential functions as well. Oh yeah. All right. So yeah, basically what I said, exponent manipulation, context and data modeling, and model validation. All right. First, let's look at exponential function manipulation. You won't use this as much when it comes to like actual graphs, but you will use it when solving exponential equations. So b to the m times b to the n equals b to the m plus n. So if we have 2 to the power of 3, where 3 is m, right? And 2 is b, times 2 to the power of 2, this would equal 2 to the power of 3 plus 2, which is 2 to the power of 5. And we can test this. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 8 times 3 equals 32, which, if you know your 2's powers, 32 is, in fact, 2 to the power of 5. Next one. If we have something inside the parentheses raised to an exponent, so like 2 to the 3 example, for example, and then we're putting that to the power of something else squared. Then you have that 2 to the power of this times this. So b to the power m, which is inside the parentheses, to identical to 2 to the power of 3, to the power of n, it's basically putting the whole parentheses on an exponent, right? So therefore we multiply the two exponents. So 2 to the 3 times 2. So 2 to the 6. These two equal each other. And we can test it again. 2 to the 3 equals 8. 8 squared equals 64. And 2 to the 6 is, in fact, 64. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and that's 5. And finally, 2 to the power of 6 is 32 times 2 is 64. So therefore, we've proven that. Next, negative exponents. So if we have sometimes you'll see negative exponents, and it's usually like you usually don't want to work with these because they're a bit more tedious. So that's why whenever we have a negative exponent, b to the negative n, this equals 1 over the exponent. Like the negative goes away when you put 1 over that. And the reason this is negative is basically negative 1, right? And 2 to the power of negative 1, for example, or anything to the power of negative 1 is going to be 1 over the number. So 2 to the power of negative 1 equals 1/2. And we can reciprocate this with the exponents. So like b to the power of negative n, it's just going to be 1 over, it's not right. It's 1 over b to the n. And again, let's test this out. So let's say 2 to the power of negative 3. Then this equals 1 over 2 to the power of 3, which is 8. I mean, the bottom is 8, so it's 1 over 8. Okay, I did not mean to do that. Let me go back. Okay, then here, radical exponent, you can't really see that, but here, let me show you. B to the power of 1 over something. Let's say like 1 over 3. It doesn't look like an exponent. 1 over 3. There we go. B to the power of 1 over 3. That equals, we have a root, it's not a square root, but the root sign. And then since 3 is on the bottom, we write 3 here. And then on the inside, it's b to the power of whatever's on the top. Since it's just 1, it's just going to be b. If this was b to the power of 2 over 3, it would be b squared cubic root 3. And these exponent laws, they're going to help us a lot when we're actually solving equations. For example, let's say 2 to the power of x times 2 to the power of 3 equals cube root of 2 to the power of 2, 3. Now this is going to combine some of our exponential laws. So we know that when we're multiplying two exponents, two numbers with the same base and a different exponent, we can just add those exponents. So it'll be the left side is going to become 2 to the power of x plus 3. And then the right side, it's going to be our rational exponent rule. So this is going to be 2 to the power of, the numerator is 2. The denominator is 3 since it's a cubic root. And now it's 2 to the power of this equals 2 to the power of this. So we can just take out the 2's and it's just x plus 3 equals 2 to the power of 2 over 3. I mean, no, not 2 to the power of 2 over 3. It's just 2 over 3. And therefore, x equals -7 over 3. Since we're subtracting 3 on this side, which would do 2 over 3 minus 9 over 3, which is -7 over 3. And just like that, we solved this equation using all of our laws. So that's how these laws help us out in finding these. Because without these laws, it would be pretty difficult to manually solve it. Okay. And here's an example of a model. 2 to the power of x plus 3 equals 8 times 2 to the x. And this is basically 2 to the 3. 8 is the same as 2 to the 3, right? So this is the same as 2 to the 3 times 2 to the x. And 2 to the 3 times 2 to the x, remember using our laws, is going to be 2 to the 3 plus x, which is equal to 2 to the x plus 3. And therefore, we know that that equation is going to be the same. Those two equations are going to be the same. Okay. Here's an example of rewriting this as a single exponential. So 3 to the power of 2x. Whenever we have exponentials multiplying each other or something, we can usually just put the base to one of the exponents. So in this case, we could just have 3 to the 3 squared and then to the x. And that's what we're doing here. And this is just using our laws again, right? Because 3 to the 2x means that it's technically 3 to the 2. And since we're multiplying it by x, it must be parentheses and then x. So this would equal 3 squared to the x, which is just 9 to the x. Pretty simple. All right. Next, negative and rational. So again, 4 to the -2x, it's the same thing. We put the actual number inside the parentheses, so 4 to the -2 to the x, and it becomes 1 over 16 to the power of x. All right. And then at the bottom here, we have one more, 25 times 16 to the x over 2. Now, is that x over 2? Yeah, I think that is x over 2. So again, here, it's a little different, right? But we have to isolate x as usual. So it's 16x over 2. Rewriting that since I wasn't sure if you guys could see it. 25. So then we factor out the 1/2 to get x alone. So it becomes 16 to the 1/2 to the power of x. Let's cross this out now. Times 25. And then 16 to the power of 1/2 is the same as, let's use our law. It's going to be 16 to the power of 1 on the inside. And then the outside is going to be just 2, which is just a square root. So 4. So it's going to be 25 times 4 to the x. And yeah, it's right. Both of these use the power property. All right, now I'm going to give you guys some questions you can work on with these laws. And by the way, let me know if I went on anything too fast over there. Went over all the laws pretty quickly. All right. Rewrite each of these as an exponential, as a single exponential. For example, what they want you to do is if it was 2 to the 3x, you would bring down the 2 to the 3, and it would become 8 to the x. So basically, they want you to do that with all these three, and then an iodine sample decays by half every 8 days. Use the power property to rewrite this function, which is a of 0 times 0.5 d to the 8, and rewrite that to become a of 0 times b to the d. So we're changing that 0.5, and we're getting rid of that 8. All right, I'll give you guys some time to do that. Then I'll solve it after. All right, I'm gonna go ahead and solve these questions now. All right, for the first one, we're just gonna separate it. So we know that 5 to the x plus 2 is the same as 5 to x times 5 to 2 using our exponent laws. So as a single exponential, this is gonna be 25 times 5 to the x, where it's just 5 being to the power of x. And that's our first answer. And then for our second answer, 2 to the 3 to the x. And remember that when the exponent is being multiplied, that means it's been put into parentheses. So like this is into parentheses 2 to the 3. And then that is to the power of x, which would make it 2 to the 3x. So therefore, our answer is going to be 8 to the x. 2 cubed is 8. And same applies here, except it's a little different. We factor out the 1/2 from the x to get 9 to the 1/2 to the power of x. And 9 to the 1/2 is the same as square root of 9, which is 3 to the x. All right, now let's look at this question. 0.5 to a of 0, which is just a constant, we can ignore it, times 0.5 d to the d over 8. We have to make that times b to the d. So we're changing the 0.5 to b, and we're removing the 1/8 from that. So remembering d, this is the same as d times 1 over 8. So we have to factor the 1 over 8 out. So it becomes 1/2, because 0.5 is 1/2, to the power of 1 over 8 to the power of d. And we're not going to actually multiply that out. So our answer is just going to be the daily decay factor, which is b, is 1/2 to the 1 over 8, which is we draw our root symbol, right? An 8 on the outside, and then 1/2 on the inside. 1/2. So 8th root of 1/2. And then that's going to be our answer to get a of 0 times b to the d. Okay. Next, we have context and data modeling. So we kind of looked at this a little bit in the start of Unit 2 in topics 2.2 and 2.3, I think, maybe a little in 2.1 too. And basically, we're looking at what affects how like exponential models look like, what exponential models look like. So A is always going to be our initial value. In the exponential functions are going to be in the form of a times b to the power of x, where b is being to the power of x and a is just being multiplied. So a is always going to be our initial value, and it's always going to be uh so like A is always going to be our y-intercept, and I want you guys to think for a second about why that is. And I'll give you guys like a couple seconds to think about that, like 10 seconds, and then I'll go ahead and explain it. So why is A the initial value in the y-intercept all the time? And it is because when x is 0, it's going to be A times b to the power of 0. And we know that anything to the power of 0 is just going to be 1. So it's going to be a times 1 whenever b is 0. So therefore, our y-intercept, which is when x is 0, is just going to be a. Do you guys see how that forms? No, let me erase that. And then B is going to be your growth or decay factor. So earlier in the last problem, we saw that it had a growth. It was something like A of 0 time. I'm going to replace A of 0 with 3. We'll say 3. And then times it said 1/2 to the power of T over 8. Now, something that could be shown by this is that uh actually I'm going to take just 3 into like uh something bigger. Let me erase it. I'm gonna change 3 into, we'll go 500. Why not? 500. Then, okay, 500 times 1/2 to the power of T over 8. Now, B is our growth or decay factor. And when B is less than 1, it's between 0 and 1, it's going to be a decay factor because as the exponential is increasing, anything below 1 and greater than 0, it's just going to keep on getting smaller. Like 1 over 2 to the power of 2 becomes 1 over 4, right? So that's why when B is between 0 and 1, it's going to be decay. An example of that is 1 over 2 squared equals 1 over 4 because it's just 1 over 2 times 1 over 2, right? We multiply top and bottom, and it's just 1 over 2 times 2, which is 4. And again, 1 over 2 to the power of 3 cubed is going to equal 1 over 8. All right, I think you guys get the gist of it. And here, let's go back to this equation. 500 times 1/2 T over 8. Now, something that could signify this is, let's say there's a bacteria that there's originally 500 pieces of bacteria, right? But every 8 hours, they're gonna half. So after 8 hours, the bacteria is gonna become 250. So T is hours, and basically, if T is being divided by anything, that just means like this happens every like that amount of time. So like, and we're gonna use exponentials in regards to time a lot. So it's good to know. So T over 8. So that means like, think about it. If after 8 hours, it's times 1/2 one time. So 500 times 1/2, then it's 250. Okay, after 16 hours, then it's done this twice. So it's times 1/2, which is 250, and then times 1/2 again, which is 125. And 16 over 8 is 2, and 1/2 to the power of 2 is 1 over 4, and 500 times 1 over 4 is also 125. So it works, right? So our B value is going to be growth or decay, and then percent change. If it's greater than 1, uh, then whatever 1 is being added on is going to be the growth or decay. So let me erase this stuff and then show you guys what I mean by that. Sounds kind of weird in words. Okay, so 1 plus R, it's going to be A times, let's say B in the form of, no, let me just write a normal equation. So like 1,000 times, actually we have one right here, 500 times 1.08 to the power of T, right? 1.08, it grows 8% every year because it's 1 plus R. And then R gives us that percent. R to the power of T. R is our rate that it grows at each year. So 1.08, that means it's gonna grow at a rate of 8% every single year. And then here, equivalent forms, rewrite base for different time scales. So this is what I was talking about earlier. Let's say like 500 times, let's say it doubles every day. The bacteria doubles every day. Then to show how much if we're using weeks instead of days, then we could do this by multiplying the time by 7. So every 1 week, it would double 7 times. So 500 times 2 to the 7. So this is days. I'm gonna write D for, actually, I'm gonna just write days. Day, and then that equals 500 times 2 to the power of 7t. All right, that kind of gets blocked out with line. 7t. And that's if it's t is in weeks. And then you guys will be given calculators for some tests in pre-cal, and they're going to ask you to do regressions to find exact exponentials. But that's much easier if you actually understand what the exponential does. So I'm not going to have you guys worry too much about that for now. So here, little tip, B equals 1.05 means 5% growth, not 105%. Just thinking simple. If we have like 100 people and we multiply by 1.05, it's gonna turn into 105 people, which is 5% growth. And it's 105% of 100, but it's only 5% growth. And if it were 105% growth, then that would become 205. And that would be 205% of 100. Okay, here's some examples. We get 2 points, 1 comma 10, and 4 comma 80. So if we just look at the ratio, we're finding the ratio to find our function, right? 4 minus 3, so this is 3 steps because it's 4 comma 80 and 1 comma 10. So 4 and 1, right? You guys see what I mean? So b cubed equals 8 because, and we get 8 from dividing 80 by 10 because it's our ratio, right? We're looking at So normally, like when we look at quadratics and stuff like that, we look at the addition and subtraction. Here on exponentials, you want to divide. So 80 divided by 10 gives you the ratio of 8. So over 3 steps, multiplies by 8. So b cubed equals 8. So b equals 2. So, and then we can plug this into our original function, which is a times b to the x, right? That becomes a times 2 to the x. And then let's have x as 1 for now. And that equals 10, right? Because it gives us that. So a must equal 5. And we can test that by using another other point. 5 times 2 to the 4, does that equal 80? And it does, because 2 to the 4 is 16, and 5 times 16 is in fact 80. So we find our function of 5 times 2 to the x. Here, 200 milligrams of caffeine decreases by 13% each hour. So 200, and then since it decreases by 13%, we're going to subtract 200 is our original, by the way. This is our A value, right? This is when time is 0. And then 1 minus 13%. 13%, we divide by 100 to get the percent in the form of decimal. So 1 minus 0.13 to the power of t, which is the same as 0.87 to the power of t. And if we wanted to model this in, let's say it still decreases by 13% each hour, but they give us time in days, then we can just multiply by 24. So 0.87 to the power of 24t, and then t in days. That way it gives us the 24 hours of the day, and it's still the same exponential. And here, just looking at an hour, is 200 times 0.87 to the 5 equals 100 milligrams. And then here's some problems for you guys to work on. And I'll give you guys a second to solve those, and then I'll go ahead and solve them right after. Okay, so problem 1, a car purchased for 25,000, which depreciates 15% per year. Oh yeah, it's gonna ask us to write the model and find V of 4 and interpret what it means, and write v of t with the monthly decay factor instead of yearly. Okay, so 25,000 is going to be our a value because that's what the value is when time equals 0, right? So 25,000, and then depreciates, underline that. That means decrease pretty much 15% a year, which means our B value is going to be 1 minus 0.15. We got 0.15 because 15% in decimal, which is 15 divided by 100, is 0.15. So, and then we subtract that from 1, and it's going to be our B value, right? Which is 0.85. I'm just switch over here. Okay, 8, 5, and then to the power of t. Just like that, we did part A. Find v of 4 and interpret. So basically, we're going to put 25,000 times 0.85 to the power of 4. And I just did this in the calculator, and it's approximately $13,050 and 16 cents. So that's going to be that. And then interpret the meaning of this. I'm just going to say the meaning. Can't write it out. It's going to take too long. The meaning is that after 4 years of purchasing the car, the value of the car will be $13,050 and 16 cents. Now, rewrite V of t with a monthly decay factor instead of yearly. Okay, monthly decay factor means there are 12 months in a year, right? So obviously, first of all, let's get what we know down. So that's going to be our A value. Our A value stays the same. It's not going to change. 25,000 times, and then our B value also stays the same. The only thing that's going to change is what it goes to the power of 2. So instead of just T, it's going to be, well, we know there's 12 months in a year. So if we're going by a monthly decay factor where T is in months, and if T equals, if this is 0.85 is when it's 1 year, well, that equals 12 months. So it would take 12 months to get 1 year. I want you to think about it like that, right? So it has to be T over 12. The reason this isn't 12T is because that would mean that after 1 month, we would like uh put 0.5, it would depreciate for like 8 years worth of it. But what's really happening is that after 12 months, which is a year, it's going to depreciate once. And uh if 12T would be if, let's say, it's depreciating by 15% every month, but you put it in years, then it would be 12T. But in this case, it's going to be T over 12. Next, we have this exponential function passed through 2 over 8, 2 comma 18 and 5 comma 46. First, find B. Okay, let's do that. So for B would be 5 minus 2 is 3, which is gives us the difference between these two. So B cubed is going to equal B cubed, B to the power of like the difference between these two is going to equal the ratio between these two numbers, which is 486 divided by 18. This is what we did earlier with that, with some similar question. So we know how to do this, right? So first, let's do the division. So 18 times 10, 180, 3, uh, yeah, okay, it should be 27. So 486 divided by 18 is going to be 27. And then that equals B cubed. Then B is going to be equal to 3. So B equals 3. And now to find our A value, we can just plug points in. Let's use 2 comma 18 first. So 3 to the power of 2 times A equals 18. And 3 squared is going to be 9, and we divide by 9, and A equals 2. So then our model is going to be 2 times 3 to the x. Let's put a parentheses around that 3. That's going to be our model. And then f of 0, remember f of 0 is our y-intercept, which is always just our a value. So this is going to be 2. Just like that, but the question solved. Okay, let's look at the final thing of the day. Model validation. So this is basically just residuals, right? Comparing linear, quadratic, and exponential models, and then quick checks on the data. Okay, first of all, this is just a quick review over here that constant differences is linear, which basically means the first difference, if it's all the same, it's different. Linear, constant second differences, then it's quadratic. Remember, this is stuff we did in like unit 1. And then constant ratios is going to be exponential, as we saw earlier today. Residual, now you guys need to remember this, that residual equals actual minus predicted. You can't mix it up that the residual equals the actual predicted minus actual, and you'll get it mixed up, right? So the analogy for this is like wrap that the residual equals actual minus predicted. You can remember it like that, or if there's another way that you guys find to remember it, then like whatever works for you. But wrap is the most common analogy that I've heard for this, and you just gotta remember that. So for example, if the actual value is 5, but a model we used predicted that it was 7, then our residual would be -2. So this is actual, right? I'm gonna write A for actual, P for predicted. We can see that it's -2. So when it's negative, the residual is gonna be it. When the residual is negative, then we can see that our estimate was an overestimate. We overestimated it. But let's say our predicted was instead of 7, it was 4. Then that would make our residual 1, and that's positive. So it looks like we actually underestimated. And okay, residuals. For the residual plot. If there's no pattern in the plot, then the actual model is appropriate. Where if there's a clear pattern, like a curve or a linear model, then like it's not appropriate. So I want to show you guys like, by the way, by model, let's say we have like points like this, right? The 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 So that's going to be like a model we might, no, just some points we have, right? A residual for, I mean, like predicted model for this, a plot for this a line would go something like this, right? Obviously, it's not going to catch all the points exactly. It's going to underestimate and overestimate on some points. And if we model the residuals for this, it would look kind of random, right? Like some are over, some are under. That would be like the model of the residuals. Whereas if it was like a bad model, let's say the model was like this, then it would just, the residuals would like go like that. It's not as good. And that's what they're showing here, right? No pattern in the residual plot, model is appropriate, clear pattern, model is not. So here is a good actual fit of the actual model, right? This proper because the residuals look completely random. This where the residuals look like an actual model, this looks like a quadratic. Yeah, it's not. It's not gonna work. Okay. And then, okay, which model is this? Okay, just looking at this, or wait, let me go back. Okay, looking at this. Okay, so this is not one where we look for constant difference. You have to recognize right away that the ratio, right? There's a ratio. 5 times 2 is 10, 20, 10 times 2 is 20, etc., right? So we do 80 divided by 40. That's going to be 2. So we write that. 40 divided by 20, 2, 20 divided by 10, 2, 10 divided by 5, 2. Okay, so the ratio of all these are the same, so it is going to be an exponential model, as we can see right here. Residual analysis. A linear model was used to fit the data above. A residual plot shows a curved pattern. So is it going to be an actual proper model? And the conclusion is the linear model is not appropriate because the residuals have a pattern. It can't have a pattern. And the exponential model is a better fit because it has constant ratios. And that therefore it could have a model like that. So like going back to what we said here, when it's just the no pattern residual plot, the model is appropriate. Clear pattern, model is not appropriate. Okay, so now two problems for you guys to exercise these skills. First problem is going to ask you to compute differences and second differences, and then find if it's linear, quadratic, or exponential using these differences, and then justify your choice. Basically saying like, why did you choose that? And then problem two, a residual plot for an exponential regression shows that residuals are randomly scattered near zero. Is it appropriate? Why? And if the residuals instead formed a U shape, what would that tell you? Okay, pretty basic questions. I'll give you guys a second to solve them and I'll explain them right after. I'm going to go ahead and solve these two questions now. First thing, before we compute differences, we have to check X. Stem 1, 2, 3, 4, 5. Okay, that's checked off. So we're going to check. Now let's compute the differences. 10 minus 4, 6. 18 minus 10, 8. 28 minus 18, 10. Okay, I'm starting to see a pattern. 40 minus 28, 12. Okay, now let's compute the second differences. Okay, I'm going to write them here since we have space there. 8 minus 6 is going to be 2. 10 minus 8 is also going to be 2. 12 minus 10 is also going to be 2. So all the second differences are constant. So therefore, it's a quadratic. We know that if the second differences are constant, then it's a quadratic, right? So we computed that, and then we said it's quadratic, and it is here, put it in text. It is a quadratic because the second differences are constant. And remember that whatever difference that is constant, let me put that back there. Okay. Whatever difference is constant, if it's the fifth difference that is constant, and it's going to be something to the power of 5. If it's the third difference, then it's a cubic, right? First difference, it's just linear. So whatever difference it is, the actual function is going to be the same power degree. Okay. A residual plot for an exponential regression shows residuals randomly scattered near zero. Okay, things I'm noticing right away. Randomly scattered, that's good. That means it's best fit. And we always want a function that where the residuals are actually near zero, close to zero as possible, because that means the predicted model is pretty close to the actual points, right? So, okay, this looks like a proper model, and then it asks us, is the exponential model appropriate? And we can say yes. And that is because, I'm going to underline, it's because randomly scattered and near zero. Those are two indicators of an appropriate model. Now, if these formed a U shape, then it would tell me that the exponent, here, let me decrease font size to the exponential model is not appropriate since the residuals are forming a pattern. Remember that if the residuals form a pattern, then the actual function is not going to be appropriate. And with that, we just covered all of topics 2.4 to 2.6. And I will be posting a unit test on unit one soon. So just stay updated for that. And with that being said, I will see you guys next class.